Hello. The aim of this video is to present to you what is considered an abstract algebra, advanced level abstract algebra topic, namely purity, at a level accessible to everyone who is interested and everyone who has undergone some sort of basic linear algebra training. Well, the definition of purity is motivated by a question of linear algebra, which is why we start out with a system of linear equations, as you see in this slide, where all the aij's are scalars, real scalars, and bk and xi are supposed to come from real numbers. So everybody you see here is a real number. But in order to put it into the context that will facilitate our understanding of the question, of the main question of this video, we will treat reals as a vector space over itself, and we will view in this system bk and xi as coming from V as a vector space and aij as being scalars of the field of real numbers. Now, the basic questions of linear algebra are those like how many solutions are there, or if there's any solution to the system at all. But our question is a little bit different. Our question is the following. Suppose V, here it would be the reals in this particular instance. Suppose V is contained in a vector space, real vector space W, and the W admits a solution to the system, which means there is a solution of n tuples, the coordinates of which are coming from W, and it satisfies the system. Suppose that's the case. Now the question is there a solution in V2? So does the existence of a solution in an overspace imply the existence of a solution in the space that we started out with, namely V? That's the question. The answer in this case, in the case of vector spaces, is easily yes. And here's a proof. So pick a solution, any solution, of the system in W. That would mean an n tuple like this one, where the coordinates vi, the wi, come from the W, the space W. What this means is when you substitute all the wi's in the respective xi's in the system, you will get the following. So this is what you get. Now, in order to find a solution in our vector space V, we are going to recall a basic property of vector spaces. There's a subspace D, say D, of W, such that D plus V is equal to W and D intersection V is 0. Let's talk about what it means. This means that every element of W, say X, is a sum of two elements, a unique pair of elements, a unique pair, I stress. One coming from the vector space V and the other D coming from the vector space D. Once again, the pair of these two elements, which in sum yield the X, are uniquely determined. Now let's apply this information to the solution, the n tuple of wi's that we picked from W, satisfying the system. So this means for each of the i's, ranging from 1 through n, we will be able to find a pair of elements di and vi, coming from the respective subspaces D and V, such that wi is equal to di plus vi. And the next thing we are going to do, we're going to substitute these encircled equalities in the system you saw a couple of pages before, right here. So we're going to substitute them right here. This will get us the following. So this is what you're going to see after the substitution. Next, we're going to distribute all the AIs into the parentheses, like so. Which will get us the following form. So we get this. Notice that after the distribution of the AIJs into the parentheses, we took one more step and gathered the D terms, the terms containing D's and the terms containing V's into different groups. There's a reason for that. Well, let us underline the D terms in orange color. This means we are marking them as elements of D, the vector space D. That should make sense, because see, all the DIs come from D, the vector space D, and D being a vector space, it's closed under linear combinations. Therefore, the underlined expressions being linear combinations of elements of D, they themselves belong to D as well. Now, so we have just marked the expressions or the elements that belong to D in each equation in orange color. Now we are going to do a similar thing for the elements that belong to V, the vector space V. Notice that these guys now belong to V. In each equation on the left side, the VI terms grouped into parentheses add up to terms of V for similar reasons. But there are other elements that belong to V that we haven't marked yet. Remember, the BI's also come from V. So the expressions or the terms underlined in red color, they all belong to V. Now remember that each element of W is a sum of a unique pair of elements, one coming from D and one coming from V. So viewing all these underlined expressions as single elements that belong to the vector space W, we see sums of elements coming from D and V in each of the equalities, M equalities that you see. If you think that elements of D are missing on the right sides of the equalities, you may add to each equation, to the right side of each equality here, a 0 as the element of D. So now we have on the two sides of each equality a sum of pairs of elements from D and V that we can compare. Because of the uniqueness that we mentioned, we must have the following. In each equality, the elements of V must match. So, for example, this guy, and I should maybe mark it a little bit more tidily. So, for example, this person here must be equal to this person. And similarly, the ones underlined in orange color must be equal to 0 each. So this is 0, this is 0, and I should maybe use a matching color that will make sense. So I'm going to use this. So this is 0, this is 0. So let's summarize what we have just found in each of the equalities. What we need is just this part of the system that we got on the previous slide, where we see only the VI's. So you see now we have a system of linear equalities, because now the VI's are definite, and VI's come from V. So therefore the n-tuple V1, V2, Vn is a solution of the system in V. This was what we wanted in the first place. So this ends the proof here. Now, we need one more thing to understand our question, namely the question that motivates the purity. So if in the definition of a vector space the term field is replaced by ring, which we know is a more general form of field, we obtain what is called a module. So modules are nothing but vector spaces over arbitrary rings. Now let us consider the linear system that we saw in the first slide in a slightly more general form. So consider, just take a module M over a ring with unity, and we're going to assume that the scalars act on the left side of the module, the elements of the module, which means this is a left module. Now consider the same system as you saw on the first in the first couple of slides. But this time, the AII's, the AIJ's come from the ring R, and XI and BI are supposed to come from the module M. Of course, the XI's are variables, but the values that they assume will be elements of M. So, next we will pose the same question as we did in the vector space context. So we will ask the following question. So our question is this. First you start out with a module N, which contains M as a submodule, and then ask if the system is solvable in the over module N, does it necessarily have a solution in the submodule M? And the answer in general stands in stark contrast with its counterpart in the vector space case. So the answer in general, the general answer is no. So why is this difference? Well, let's try to remember what enabled an affirmative answer in the case of the vector spaces. So to see that, we will remember this basic property of vector spaces and subspaces. It is this property. It is the existence of such a D as is shown here for each V, for each subspace V of a space W. So you cannot say the same thing for modules. You want to give an example? Here's a simple example. Take, for example, the ring of integers modulo 4, call it R, and let our module M be the multiples of 2, and the module containing M will be R itself. Now it's an easy exercise to verify that there is no submodule D of n such that m plus d is equal to n and m intersect d is the trivial submodule. Now this situation immediately prompts the question as to when systems of the solvability of a finite system of equations over M in an over module, say n, imply the solvability in M. So I'm going to write this question. So this is the new question. What are the conditions that ensure that any finite system of equations being solvable over n is again solvable over n? Any finite system of equations being solvable in the over module n implies the solvability of the system in the module M. So when is it true? We have a special term that describes the situation that the situation where this is possible, where the answer to this question is affirmative. So the situation that admits an affirmative answer to the previous question is when we say that the module M is a pure submodule of N. Now we know the basic definition of purity and how it is motivated. So in the upcoming videos I will continue this discussion and try to give you more information and discuss maybe some examples. Thank you for listening.